So today we're going to be hearing from Justin Daley. He's going to be talking about exploring for IOCG and discovering rare earths and diamonds on the Kapuskasing in Northern Ontario. Justin is a professional geoscientist with over a decade of global experience in grassroots and early stage mineral exploration. He's obtained a master's in mineral exploration from Laurentian and a Bachelor of Science from Queen's University. He's also recently completed a Harvard Business Analytics program, which focused on digital transformation of business, data analytics, and applied AI. He has experience in throughout the Americas, Canada, US, Mexico, Peru, and Chile. I'd like to welcome Justin.
Okay, thanks. Thanks for the introduction, and thank you, Michaela, who I went to undergraduate at Queen's was many years ago, not so many years ago. It's good to be here back in Sudbury, and thanks everybody for coming out. And for those of you who are online, thank you as well. So yeah, we'll get started here. Cautionary statement, if I make any forward-looking statements, pretty much everything here is in the public domain though. The agenda for this talk is going to navigate the journey of taking blue sky exploration concept and executing it through meticulous testing on geophysics and drilling, revisiting all the data, and remaining open simultaneously with those serendipitous discoveries that happen along the way. Very often you don't find exactly what you're looking for, but it's good to look at all your data to make sure you haven't missed anything. So we'll start out with that formulation of the IOCG model on the KSZ. We'll touch on the Renoke exploration program, dive into the heclokilmer carbonatite exploration, moving from the understanding of IOCG into iron oxide apatite systems, how we used new tools to explore faster and more effectively under that covered terrain in the James Bay lowlands, as well as my own personal move to get updated on rare earth element deposit models and their mineralogy and how important that can be to the economics of a rare earth element deposit, as well as finally moving on to Northway, where we return to our IOCG target model and found a kimberlite. So some of the main talking points I want to get across without getting too deep into the minutiae of the geology is to try and tell an exploration story about the importance of using methodological exploration to really try and get the most out of your geophysics, get the most out of your historic data, make sure you're getting as much as you can out of all the data that we're now inundated with these days, and all with the goal of targeting blue sky exploration where not, I feel, as much money is being spent as could be spent. Most money gets spent these days on brownfields exploration. And to meet the demands of the green transition, which we all hear is coming our way, I feel it is important to go after these blue sky opportunities. When looking through these opportunities, it's important to understand why or how these discoveries hadn't been made in the past in these areas. And a lot of the time, you want to try and tell yourself exactly why that might happen. It could be because the technologies or the mineral deposits didn't exist that do now. So IOCGs really didn't come onto the stage until the 2000s, after the discovery of Olympic Dam, Carapacina, etc. So workers in the 1970s and 80s might not have known to look for specific vectoring elements. Further, as we're in a difficult market cycle right now, it's important to remember what was happening in the past, specifically in the 1980s and 1981. Higher interest rates and inflation killed a lot of exploration programs. Didn't mean that they were bad projects. They just hit a brick wall. And on that theme of blue sky exploration, you miss 100% of the shots you don't take. So it's important to get out there, test your targets, and try and learn something. VR led by Dr. Michael Gunning. He's been in the business for 30 plus years, has had a number of successes in uranium, and started VR Resources, which stands for his favorite ski from the 1980s, the Volkel Rentiger, which was the epitome of cost-effective, high-technology race skiing. He built the company. I was the founding geologist back in 2017 to go after this project in Nevada called Bonita. which we presented at the GSN symposium a few years ago. We did some geochronological work, which placed Bonita in the late Jurassic. It's the southern extension of the Quesnel and Stickenia arcs, shown here on the map. So really, this is the southern extension of some of those copper gold porphyry systems that you see in northern BC in the Golden Triangle. At 165 million years old, it's a little bit younger. What happens at Bonita, though, is that there are these large speculite breccias with copper and gold mineralization, as well as uranium and rare earth elements. And so it became quite clear to me that I needed to learn about this transition from copper gold porphyry systems through to IOCG systems, how they linked, what are the fluid dynamic processes at work there, and how can we use that new learning to explore in a new region. And so Mike dug this out of his filing cabinet in 2018, and I got to work on the historical compilation work. The main idea here was that there is an unexplained copper or chalcopyrite, gold, and fluorite in alluvium in the Paleozoic platform of the Kapuskasing structural zone. This is in northern Ontario, north of Timmins. Really, this grouping of heavy mineral grains, which initially came from kimberlite exploration work, and people, of course, weren't looking for chalcopyrite, gold, and fluorite grains when in the search for diamonds. But taking this information and saying to ourselves, what could be the ultimate source for an alluvium mineral grain anomaly such as this? And the first thing that came to mind, given our research, was IOCGs, where fluorite is very common, and of course, the mineralization chalcopyrite and gold. So zooming into this area, we started to learn as much as we could about the Kapuskasing structural zone. It's roughly 2 billion year old failed rift beginning around 1.9 billion years ago through to the Keweenawen Mid-Continent Rift event around Lake Superior. There's further magmatism along the KSZ 1.1 billion years ago, all the way through to the Jurassic and Cretaceous, coming up this very deep-seated crack, crustal thinning occurring here, 600 kilometers long, and roughly, we figured 10 to 30 kilometers of uplift potentially along the northern side of the KSZ. Sure.
Sorry. Yeah, I know. Sorry, guys.
Okay.
Sorry.
Perfect. Okay. So here's a zoom into the Kapuskasing structural zone. It's generally northeast-southwest trending, and there are several alkaline and carbonatite systems along the trend. Now, alkaline intrusions are generally thought to be potentially related to IOCG mineralization, and especially the right chemistry to have porphyry, copper, gold, IOC sort of continuum of hydrothermal activity associated with them. So we figured maybe a magmatic source such as these would be something of interest. And because we have these chalcopyrite, gold, and fluorite grains sitting on top of the Paleozoic and Cretaceous successor basins, denoted by this sort of pale gray going northwards, we figured that there must be a younger age of intrusion that could have been the cause for this sort of mineralization in the alluvium. And we really zeroed in on the Great Meteor Hotspot Track as potential here. The Great Meteor Hotspot Track trends from Rankin Inlet, where it is the source of magmatism for kimberlite pipes there, as well as in Attawapiskat around 180 MA, that's the source of the Victor Diamond Mine. And then it travels southeastwards towards the Oka Carbonatite Complex outside of Montreal, and then onwards into the Atlantic Ocean, where it's creating seamounts to this day. So the thinking was that there is a magmatic hydrothermal system coming up one of these deeply seated structures, penetrating through the Paleozoic strata all the way to a paleo surface, where glaciers could then spread around those mineral grains. And in that initial research on IOCGs, we were also thinking about places in the Earth's crust where an IOCG type system might be likely. There are back arc basin environments such as Candelaria in Chile, where there's a well-noted IOCG and iron oxide apatite mineralization. But the bulk of mineralization occurs around a thinning crust on the edge of a craton, potentially in a failed rift environment, such as where Olympic Dam was discovered in a Mar-type setting. This is where you have partial melting of the subcontinental lithospheric mantle, ponding of that melt, volatile transfer, and then movement of those magmas and hydrothermal fluids upwards into deposits like Carapatina or Palabora or Salobo in Brazil. And so really dreaming big here, we decided to settle on a model like Carapatina. Why not? Let's look for something like this. This was a world-class discovery back in 2005, really on following up a 2.5 milligal gravity anomaly. It's this circular anomaly right here. The prospector, I'm told, drilled 2 holes into this anomaly. He put on a second mortgage on his house, I believe the story goes, without telling his wife. And upon drilling the second hole, discovery hole of 355 meters at 1.25% copper and half gram gold. Now that's under roughly 500 meters of cover. So imagine waiting for bedrock to appear on that drill program. Roughly 2 years later, hole 50, 905 meters at 2% copper and 1 gram gold. So with a deposit model and world-class nature like that in mind, we're looking for a very large magnetic and gravity anomaly in this general area. And we're thinking about the glacial ice directions, which way they're moving and which way they should or could have spread mineral grains around in the glacial period. And of course, thinking about those rivers, the Missinaba, Matagami, and Abitibi, then taking those glaciated grains back along the riverways. And of course, it basically lands you right in the same spot on top of the Paleozoic strata. So in looking at the OGS magnetic and gravity data, the gravity data is really quite sparse, but it does tell you quite a bit about the KSZ and uplift and potential gravity sources that might be related to intrusions or, in fact, mineralization. You can see that KSZ with this dashed white line I'm showing here now. And you'll notice that there's a high density anomaly on the northwest side. This is that uplift I talked about earlier, where you have granulite facies rocks in contact with green schist facies rocks on the southeastern side. When we layer in the geological domain boundaries, as well as the Paleozoic and Mesozoic basin boundaries here, we get an idea of where we are located and where we might start looking for an intrusion or a geophysical signature for an intrusion. And in looking at this map, it's pretty clear there's something funny happening here and here, roughly co-spatial magnetic and gravity anomalies. So we select this target. It seems to be a magnetic amplification along pre-existing structures, the Matachwan dike swarm trending roughly north-northeast, and the Kapuskasing dike swarms traveling roughly east-west. So something strange is happening to the magnetism in this general area. And we go back to our model thinking potentially this could be something that's coming through that Paleozoic strata all the way to the base of Till. So there's that magnetic anomaly outlined here on a satellite imagery. All these teal pins are 1981 lignite coal exploration holes. They actually had the foresight to do heavy mineral analysis on the till overlying the Cretaceous Basin in all these drill holes. And in fact, they found chalcopyrite in this general area as well in those drill cores. So, or in the till. So this gave me a pretty strong indication that maybe there's a source for that chalcopyrite in this general area. And it had never been drilled before, most importantly. And 12 kilometers to the south on the Matagami riverbank, there's this very strange rock with these magmatic hydrothermal looking textures. There's roughly 1,000 ppm phosphorus, but it's almost entirely hematite with some pyrite replacement of some clasts. Very strange rock. I've got it here in my backpack if anybody wants to tell me what it is. I know we all like looking at rocks. So in pretty quick order, we get to work exploring at Renoke with that sort of systematic approach to mineral exploration, thinking about the physical attributes of our target, of the deposit model, and then executing in quick succession to get to a drill-ready target, and then, of course, drilling it. So we started out with a gravimetric and magnetic survey to get more high resolution data over the targets. We followed that up with AGI soil gas, which basically entails putting a inert charcoal capsule underneath the muskeg into the underlying marine clay and waiting for that capsule to absorb sulfur, carbon compounds, and volatilized metal compounds. And so you let it sit there for roughly 3 months. And then finally, following up that work, a Quantec Titan 24 IP survey. These are all technologies that did not exist in the 1970s and 80s when people were initially drilling in this area, and we hoped would help us see through that thick cover for a source for these chalcopyrite and gold grains. And then, of course, 3 drill holes to test our best targets, culminating in the pandemic in March 2020. The results of that initial gravity survey, I'm going to go through this pretty quickly because we didn't find anything. There's that initial gravity response, so 2.5 milligal gravity anomaly, very similar to the one at Carapatina. It's large. It's roughly 1.5 kilometers across. Those are some initial test hole ideas. When we ran the magnetic and gravity inversions separately, we found that the gravity and magnetics sort of fit together like a jigsaw. They're starting to become this strange correlation here. They're not overlapping, but they're correlated. We can see the outline of the core of the gravity anomaly here. And very faintly, you can see that the soil gas response was actually quite good over this general area. We're seeing carbon, sulfur, we're seeing copper, gold, and uranium in parts per trillion, but anomalous over this general area. So I'm getting quite excited at this point. And we follow that up, of course, with the Titan 24 IP and see a chargeability anomaly right on top of the gravity anomaly. So at this point, I'm thinking it's begging for a drill hole. We get out there in November 2019 and drill through 195 meters of Paleozoic sediment, and then eventually some Silurian sandstone, which really messed up the drilling. A couple of drill holes later, and the pandemic happened. I said, let's just call this and go back to square one and start thinking again. However, we did see some hematite speculite veins in some of the basement geology, as well as this singular fluorite vein. So something strange is happening there, but it's at 195 meters, it's probably not the source of our chalcopyrite and gold grains. So back to the drawing board, we start to think about what could be a different host for or source for these chalcopyrite gold grains. I realized that a lot of these alkaline carbonatite type intrusions, they're in exposed craton. They've seen quite a bit of work over the preceding 50 years. And there's only really one of them that's north of the cover, the Paleozoic cover, and has only had 7 drill holes and 0 work since then. And that is the Hecla-Kilmer anomaly, which unfortunately is right under this Wabigoon-Quetico suture boundary. Here it is in finer detail. It looks like a classic alkaline intrusion. You've got an outer rim of more magnetic material and an inner core of less magnetic. There's only, those 6 drill holes in the alkaline complex, and there's 2 on the margins into kimberlitic type pipes. And I think that this is a promising target because through those 6 very shallow drill holes where the logs essentially say basic breccia, they had no conception of alkaline intrusions in the 1970s, or at least this company didn't. And we're looking at the base of till at being roughly 40 to 50 meters, and it's exposed to glaciation. So there's a probability that there could be chalcopyrite gold and fluorite grains coming from this alkaline complex and being spread around the region by recent glaciation. And in coming back to our IOCG research, I realized that one of the models, one of the IOCG deposits shown on here, Palabora, is in fact a carbonatite. I believe it's the only carbonatite with IOCG mineralization, and it's fairly typical. It has an outer rim of pyroxenite, and it goes into an inner core of phosphorite. Phosphorite actually comes from the Phosphate Corporation, which was mining apatite out of the Palabora area initially. And there's 900 million tons of 0.6% copper in this carbonatite pipe. A phosphorite, by the way, is a rock with a lot of apatite, a silicate such as olivine, augites, phlogipites, usually some calcite and an iron oxide. And so there's also a a zonation, an inward zonation into the chalcopyrite mineralization. And one of the most interesting parts at roughly 600 by 900 meters in size is that the open pit correlates with an RTP high to RTP low reversal. I thought that was pretty interesting because we see the exact same thing at Hecla Kilmer in the Pike Zone in the northwest area, and some of the most interesting drill hole logs coming from this area. The historic core, though, was left in the bush for 50 years. It was covered in muck and grime, and the prospectors, Kevin Keevy and Gary Peacock, who went out and retrieved that drill core, they brought it back and they put it into a cement mixer to try and clean off some of that muck and grime and moss that had been on it for 50 years. They put some clean sand and they rotated it. And when they panned the sand at the end, they actually found that there were gold flakes. So there's gold flakes coming off the surface of this core. There's chalcopyrite and fluorite in veins. We've got all three ingredients for this IOCG target. So I convinced Mike, let's acquire this property and get to work with our systematic approach to exploration for an IOCG on the KSZ. In quick succession, we try a geophysics technique, we drill test it, go back to the drawing board, more geophysics, more drilling, more geophysics, more drilling. In this case, VTEM plus in 2020, ground gravity following up on density anomalies in that initial drilling, and eventually a high-res drone magnetic survey to help us undercover identify some of the controlling structures in this complex. But of course, because we all like looking at things in 3D, we did a magnetic vector intensity inversion, and that essentially, if there are any geophysicists in the room, I'm sorry, you basically take the absolute value of the magnetic response and invert that into 3D space to try and show where the bulk of the magnetism is coming through. And on the north part of the complex, the Pike Zone, we drilled our first couple test holes and saw some truly ridiculous breccias, 600 meters of biotite altered brecciation, multiple heterolithic rocks in here, a lot of carbonate fragments, a lot of very strong biotite alteration. With my background in porphyry copper systems, this amount of shreddy biotite was truly staggering. I had no idea what it was either because I'd never really studied a rare earth element system. But we were seeing veinlets of magnetite, pyrite, and chalcopyrite. Some of these open space veins have pyrite, chalcopyrite, hematite, mossy phlogopite sitting on top, and fluorapatite growing into open space. And we're realizing that there's the potential that we're on the edge of something potentially. We don't really know what we're looking at. So we decide to ship the core after the drill program down to Sudbury, to SGS in Garcon, to do XRF scanning through Mineralized without spending the full whole rock analysis money to analyze every inch of core. We actually get more information with less money using the XRF. Very useful for early stage exploration, I think, because you get a broad spectrum of trace element indicators to help you start vectoring and deciding if you want to sample and where you want to sample. I also realize that X-rays are, when penetrating rock, can tell you about the density or specific gravity of that rock. And I saw very early on the correlation between density, apatite, and magnetite are very dense rocks, and things like lanthanum. And I'm using lanthanum here because I've read that it is a good vector for IOCG style mineralization. We also see that copper spikes north of 1000 ppm in several of these veins, and we see that gold is also spiking in similar veins, not always co-spatial, but when we do the gold assay on the rocks, we realize that one of the magmatic phases that I've come to call a phonolite, for lack of a better term, actually regularly has 10 to 70 ppb gold in it. So maybe there's a gold-rich magmatic source somewhere in this complex that we can target. But at this phase, I'm starting to realize that we might have two different things happening. There could be an IOCG system in this complex, but far more likely is that we have an iron oxide apatite system. IOCGs typically precipitate out mineralization around 400 degrees Celsius, whereas iron oxide apatite systems are much deeper and hotter, precipitating out their mineralization around 600 degrees Celsius. And they tend to be a continuum, and this is after research near Candelaria in Chile. because you have a broad array of erosional environments in the Andes there. Either way, we quickly zero in on these gravity rare earth element anomalies, realizing that they are spatially quite extensive from the near surface environment of hole 4 all the bottom of hole 2. We're seeing what turned out to be good grades of rare earth elements, tens of meters at 1% total rare earth oxide. And we follow that a correlation of gravity up with rare earths with a dense gravity survey over most of the complex, the areas of interest that we've identified. Quickly seeing that there is a core of high density directly adjacent to hole 2 and hole 4, where we're seeing the interesting rare earth element mineralization. And I'm starting to think maybe we just missed the big thing, the elephant in the room. There seems to be a dilational, extensional environment to or control to the gravity anomaly. And it's actually sitting right on top of that RTP high to low transition that looks so interesting at Palabora. Before we do any more drilling, though, because I'm realizing that we have rare earth elements on our hands, I need to start to understand what controls that mineralogy along with all the chemistry, geochemistry that we're collecting. Hole 4, we have a very different look from hole 2 at the bottom. In hole 4, we see very large prismatic grains trending into a massive apatite with acicular magnetite. I don't know how many of you have seen acicular magnetite growing into what I feel is a quenched vein environment. Beautiful textures to see, and also chalcopyrite and pyrite associated with this. So already I'm starting to think that maybe this is my focus. With some QuemScan work, I learned more about the rare earth element mineralogy. We find that most of the light rare earths are hosted in the apatite, but we're actually seeing some interesting heavy rare earth mineralization, predominantly in a mineral called monazite, which is, of course, a phosphate, naturally suited to be sitting inside of apatite. There is a little bit of bastosite in this zone, but it's predominantly monazite. And as I'm starting to learn, as I know now, having a very simple rare earth element story is imperative for the economics down the road of these systems. In comparison to the bottom of hole 2, we're seeing finer grained alteration in primary magmatic minerals here. There's a lot more calcite. The grades are similar here, but a little bit lesser than that interval at the top of hole 4. And I'm wondering what this greenish alteration mineral is that seems to be pseudomorphing after hexagonal biotite. And it turns out here, and most importantly, that the rare earth element mineralogy story is a lot more complicated. We have bastosite, syncosite, and a whole host of other carbonate and phosphate rare earth minerals. So not as desirable from a rare earth element economics point of view. Also, interestingly, we see that some of these hexagonal grains are replaced by sodic pyroxenes and amphiboles. So different morphology, different textures, and different overall mineralogy, but roughly similar grades. And around this time, I'm starting to get into research on what is controlling rare earth element movement in these carbonatite systems. I stumbled upon this wonderful paper where Mike Lannenberg has done 4 capsule runs from high temperature, high pressure, and reduced them all the way through and quenched them. Right away, I noticed that there's more of these acicular grains in his QuemScan imagery. But most importantly, I'm starting to see a relationship between the amount of sodium and potassium. And I'm thinking back to my sodic pyroxenes and amphiboles in the bottom of hole 2 and the tons of phlogopite and potassium phenite I'm seeing at the top of hole 4. And I'm learning now that those different changes in alkali chemistry have impacts on the rare earth element zonations and styles of mineralogy based on this research. And they also affect the solubilities of rare earth elements. But of course, as we proceeded to drill out this project, I find that my efforts to classify things neatly using chemistry are impeded by the crazy mobility of all your trace elements in these rocks. When your ore minerals are the trace elements you typically use to classify rocks, things get a little bit sketchy. So we apply more technology to the exploration effort. More specifically, we use Geologic AI's XRF plus shortwave infrared scanning technology, as boosted with artificial intelligence, and we begin drilling in earnest through 2022 to try to explore for more of this high-grade rare earth element mineralogy, keeping the door open for some IOCG mineralization as well. We get more or less real-time data from the Geologic AI system. Basically, the core comes in and the next morning you've got calibrated XRF results for that drill core. So you can take your notes from the prior day, your logs, and compare them with XRF chemistry and really start to vector in real time towards where you think your mineralization might be, and then plan your subsequent drill holes around that new thinking. And in real time as well, you can start to group together your XRF and your shortwave infrared, going after mineralogy such as the phlogipites and biotites, as well as the chlorites and things like that, using different wavelengths and using the intelligence of machines to do a lot of the legwork to look for naturally existing correlations across. So I use this program called Orange initially to concatenate all my drill logs, all the XRF data, SWIR data, as much mag-sus physical property data as I could get my hands on in real time, and use this to start to look for groupings in the rocks, because early on I literally had no idea what I was looking at or trying to log. And through the use of these tools, I was able to learn more quickly, more rapidly, what the correlations were, maybe things that looked different texturally, but had similar chemistries. And with that data in hand, making better exploration decisions as we go. So this tool called Data Mosaic from CSIRO in Australia uses waveform tessellation to look for abrupt changes in groups of elements, and then bins them into different domains, scaling from very fine to coarse. And you can think of these as being a lumper or a splitter when you're logging for. On the far right, you have large domains. Maybe this is like a felsic rock, and this is a more mafic rock, and something's happening in between, like a fault gouge zone. But on the minute detail, you actually can log down to meter wide dikes, and a lot of these actually were quite accurate. Using that data and advancing it, I was able to correlate certain groupings with rocks and rock groupings that I had logged. And then from there was able to make inferences based on thicknesses and intensities of alteration and the XRF response, and actually vector in real time while we're in a drill program towards better drilling, and eventually a intersection, which is hidden in here, 361 meters at 1% total rare earth oxide. So using technology in real time on a drill program, literally called up my CEO and said, hey, I want to drill a hole this way because of what I just saw over the last couple of days drilling over here. It was a good idea. We spent $200,000 more than budgeted, and I actually kind of got in trouble, but it all ended up okay. At the end of the drill program, now trying to work with the whole host of whole rock and total trace element analysis from SGS and ALS to try and get a sense of, what actually happened on that drill program. How can I categorize and understand these rocks, both geochemically and from a mineralogical and whole rock point of view? Again, though, there's a lot of trouble dealing with the vast amount of calcium carbonate in the system, as well as the phenites, where you basically have whole rock replacement by phlogopite. Really screws up your whole rock geochemistry. But removing a lot of that data, coming back to a least altered analog for each type of rock type that I thought I'd seen, I'm realizing there's an easy story here based around fractional crystallization in a magma chamber, where we're moving from an outer rim on the complex of hydrolite, a more mafic rock. This is essentially equal parts nepheline and pyroxene. Moving down this diagram into the center of the complex through K-spar hydrolite porphyries, a nepheline syenite. These white crystals are acicular nepheline, and then into a much coarser nepheline syenite. And in historic core, we see what the center of that complex actually looked like. So a full story of fractional crystallization in the center of the complex. But still, we were sort of left unexplained what happens over here in the Pike Zone. Why is there this large magnetic reversal? And I feel that the reason there through the logging and subsequent geochemistry is that there is a magma recharge. Cross-cutting all those previous units, we have a whole new set of units that also go through a fractional crystallization range from more mafic again through to more felsic. These more mafic rocks, though, which plot in the meltigite and izolite ranges, are actually what appear to be the causative intrusions. These are the ones that have the elevated gold, and they're most intimately associated with the phosphorite mineralization of rare earth elements. But of course, these are the most altered as well, so that made things interesting. On to the most interesting part. In a carbonatite, you always want to look for all that calcium carbonate or phosphorite. Sovites are predominantly calcium carbonate, less interesting rocks. In a lot of other rare earth element systems, it's typical that you would see bastnasite associated with a sovite. At Hecla-Kilmer, though, we're actually seeing most of our rare earth elements associated with apatite in the phosphorites. And it's here at this particular interval where I was pleased to see that we actually see the transition from sovite and then thin wisps of pinkish apatite here in this rock. So we're seeing the transition from sovite into phosphorite. And then as we move that drill hole over after learning from the XRF and shortwave infrared in real time, we started to target towards these chalcopotasic phosphorites. These chalcopotasic ones have actinolite in them, beautiful needle-like actinolite growing in here along with apatite, but still quite fine-grained, a lot of calcite, not much in the way of extensional textures, but still we do see these big, beautiful, and I have this rock with me as well, quench-textured magnetite, where you're actually, I think the magnetite is just growing quickly. It's fitting where to put the magnetite in behind it, and so you get interesting calcite. And then again, inwards here, again into that potassic phosphorite, where we see prismatic margins, and then quench textured magnetite and phlogopite growing into that extensional open space with massive apatite and the monazite mineralization that I've learned is important for the economics here. This picture should actually be a little bit longer. You actually see several steps along the core length, which tell you a lot about the extensional nature of this mineralization. You can see kinematically how this rock opened up to create space for that apatite-rich fluid to move. Is it a melt? Is it a fluid? I don't know. It's a little bit of both, and it's moving into that open space at depth and crystallizing rapidly. And that's essentially what you see in the in Michael Annenberg's paper. So this, again, is hole 13, where we had vectored in during that drill program and eventually extended the hole. And just to confuse things a little bit, there's actually a gram gold with 2% total rare earth oxide in the very last 2 meters of this drill hole. I still haven't seen the gold in that piece of core, but it's interesting to note that there's still gold moving around with things in this system. We don't know where it's coming from, but at this stage, we're firmly moving along with the rare earth elements story at Hecla-Kilmer. We're trying to learn as much, again, about the mineralogy, because with 17 different ore elements, you want to make sure you're focusing on the right ones. There's 4 of value or of greater value, and we've called these the permanent magnet rare earth oxides. These are neodymium, dysprosium, terbium, and praseodymium. 2 of those are heavy rare earth elements, and they typically are a lot harder to find. They don't occur in bastnasite. They are much greater value because they are not mined in great abundance around the world. And the main rare earth element deposit, Bayan-Obo, provides roughly 80% of the global supply of rare earth elements. The reason why we like Hecla-Kilmer, though, and we continue to push it forward, is because of this unique mix and the focus on monazite in this carbonatite system. There is more terbium and dysprosium as a ratio of the total rare earth oxides compared to other operating mines in the world. Bayan-Obo, Mount Weld, and Mountain Pass are higher grade, but proportionally they have less heavy rare earth oxides in them. Moving on, though, we haven't lost sight of our IOCG idea on the KSZ. So we zero in on a last and final target to date, and that's Northway. Northway is actually halfway between Hecla Kilmer and Renoke. It's in the same general area. And while we're working on Hecla Kilmer, we fly a drone magnetic survey here to try and outline more of the magnetic controls or potential structures controlling this weird 1.2 kilometer cross magnetic anomaly. It's a magnetic low, it's big, it's sort of got these diffuse margins on one side and very strong boundary on the southeastern side. I think it's too big to be a kimberlite. There's chalcopyrite in the alluvium samples from 2000 and in the top of the lignite exploration holes from 1981 in the till. And there's placer gold. All of these in creeks draining out of the Northway area. There's a drill hole just off to the southwest here where we figure there's roughly 100 meters to bedrock. So at the very least, it's going to be a relatively easy hole to get to basement, but I'm hoping that it's coming through the Paleozoic strata to the base of Till. So we set up there a year ago now and start drilling a vertical hole. And it wasn't until 246 meters later, with the drillers complaining, that we eventually hit basement. We see these weird green cobbles in the basal conglomerates. We see this weird green mudstone. And the drill foreman actually comes up to me. I was inside working on my AI system, and he says, "Justin, I think you have a kimberlite here." I say, "What? How?" This drill foreman has been working in the Northwest Territories for Rio Tinto for a number of years, so he knows what he's talking about. I call in some experts, and while we're waiting for them, I'm starting to think about, what are the geological controls on a kimberlite being here under 240 meters of cover? It means that this kimberlitic intrusion with a preserved crater facies shown here, we've got the kimberlitic mudstone, we've got a debris flow. This is a preserved kimberlite crater. That means this kimberlite is Paleozoic in age. It's older than the Great Meteor Hotspot Tract, the Victor and Kirkham Lake kimberlite clusters. How do we explain this? That there's no real known source of magnetism around this time, other than perhaps something associated with the Ottawa Bombshare grabens or something like that. And it turns out there's actually Don McLennan found a nearly 1 carat diamond in the same stratigraphic horizon in the Abitibi River, 30 kilometers to the southeast. So maybe there's a correlation there. Who knows? That's wild speculation on my part. In any case, the kimberlite experts come along and they start to teach me as much as they can about dunites, websterites, eclogites, and looking for kimberlite indicator minerals in your core. We start to outline several different phases of pyroclastic kimberlite, a lot of beautiful magma clasts and lapilli, and of course coherent kimberlite phases as well. So a highly dynamic diatreme breccia pipe. We come back in June of this year with more money to test the center of the magnetic anomaly to get enough material. Initially, we only had around 40 meters of core, very altered. So we decide to get around 1.3 metric tons from 460 meters of kimberlite drill core to test for microdiamonds at SRC. Much of that material looked like this. And lo and behold, this September, October, we announced that there were in fact diamonds in this kimberlite pipe. One in the crater facies of hole 1. You can see the very thin penetration into the kimberlite pipe there, and then 4 more over in hole 3. We've analyzed the phlogopites in the magma class and in the matrix. They plot within the kimberlite field on this titanium aluminum chart. It looks like, by the nature of the phlogopites and a lot of the other indicator minerals and just the chemistry, that this is coming from a metasomatized subcontinental lithospheric mantle. And there are microdiamonds. So we're checking many of the boxes for diamond exploration. It's not your typical kimberlite as compared to many of the mines in South Africa. Turns out most Canadian kimberlites are sort of atypical. But what might in fact be happening here is something more like Atawapiskat, the Victor Diamond Mine, is in the center of the craton and it's traveling the furthest, and it's a more standard type 1 kimberlite. But perhaps what could be happening at Northway is that we're sort of heading into a thinned crust environment, and you're getting more into a lamproite diamond type environments, such as the Argyle mine in Australia, which is one of the largest producers in the world. And of course, that's heading over on your way towards an IOCG fertile zone on this schematic diagram from David Groves. So subsequently, and this is the last side, realizing that we had a new age of kimberlite intrusion around the KSZ, we decided to go after as many of these magnetic lows as we can find in the area, and then also just stake everything in between Northway and our camp at Otter Rapids in case there are any kimberlite dikes or events hidden within the complex magnetics of that region. We also staked a couple of these bent elbow kimberlite anomalies, and I hear that the original did you stake them yourself, or one of the original team members? You staked it. Yeah. Okay. So they were on this back in 2013. They didn't drill all the way down to 243 meters to hit the kimberlite. So really just continuing along the same great ideas and great work. I did it accidentally. They had the idea. So there you go. That's the end of the exploration story. We're still looking for the IOCG, but in the meantime, working on rare earth elements and diamonds. That was a lot of material. I probably went longer than I'd hoped to, but if you want, email me. I'll send you slides. We can discuss. Any questions?
What's next?
Get through this tough market cycle, raise some money, and magnetic surveys for the diamond field. And at Hector Kilmer, it's simply a matter of drilling our targets. But at this stage, it's difficult to raise money right now. We're working on it. We've got a project in Nevada as well that's a copper moly porphyry system we hope to drill in the spring. Yep.
Great presentation.
Thanks.
She mentioned the different species of the REEs and why you want, and you mentioned the economics. Perhaps for some people not familiar.
Sure.
And we'll on that.
Yes. So,
Can you just repeat the question?
yeah. The question was, what are the different species of rare earth minerals? Why is it important for the economics? Basically, when you're looking at rare earth elements deposits in Canada, the major hurdle has been mineralogy. If you have several different minerals you need to process, you have several different metallurgical processes that you then need to deal with. If you have allanite, which is a heavy rare earth element enriched mineral, it's actually a mica. So you have a different type of cracking process for that as compared to a phosphate, as compared such as monazite, as compared to a carbonate or fluorocarbonate like bastnasite, parasite, syncosite. And then there's a whole host of other ones, fergusonite. If you have a complicated mix and you don't understand your metallurgy, your mineralogy very early, you might as well just stop spending money on the project because it gets very difficult and expensive. No matter the value of the rare earth elements, if you can't separate them, they're basically worthless. It'd be like having 15 different copper minerals, and some are sulfides, some are oxides, some are silicates, and you're hoping to get it out of all of them. It is not economic. So the focus for VR for us was on monazite because it is enriched in these heavy rare earth elements and the cracking process. They're actually building a plant at SRC. SRC is doing everything these days, apparently, rare earths and diamonds. So they've been good to us. They're building a monazite extraction facility. The first rare earth elements to be mined globally really came out of monazite sands. So these are placer deposits of monazite where you just dig that up rather than look for the initial source. So there is a focus on monazite as a source material. And as I mentioned in the presentation, bastnasite, parasite, syncosite, which are all fluorocarbonates, are the predominant mined source at Bayan-Obo, which is an iron oxide apatite system, Mount Weld, which is a carbonatite that actually has a bit of a monazite placer layer in it in Australia, and Mountain Pass in California is bastnasite as well, with a whole host of complex minerals that aren't being fracked at the moment. So I think like extract or recovery rates are around like 70% if you're lucky in a lot of rare earth element systems, depending on your mineralogy. Highly variable, very confusing, steep learning curve.
You should be able to steal his omics and on top of your timberland and silver.
Yes, so we see late Silurian sandstones, but the basin, let's see if I can find that section. The basin is as old as Ordovician, further north into the center of the Hudson Bay basin. The James Bay, though, is a little bit younger. Yeah. All the way back. Any other questions in the meantime? There we go. Yeah, Ordovician is the earliest. Yep.
Are you finding any radioactivity?
So there is monazite naturally has thorium in it. Most of that, the thorium though that we see is locked up in monazite. It's a refractory mineral, so there is zero. It's a not naturally radioactive material. It's NORM, not NORM is the acronym. Not it's NORM. It's not.
It's sorry.
Yeah. Sorry, was it a lot? Oh yeah, it's thorium. Yeah. So there is like maybe a couple hundred ppm max of uranium. We don't know where that's sitting, but that was one of the first, given our CEO Mike's background in uranium, he wanted to make sure that we weren't radiating me or any of the other people working on the project. So once we realized that we did have that thorium uranium, we tested.
Thank you.
Well, thanks for inviting me.
We appreciate you coming all the way from Toronto.
Oh, it's great to be back in summer.
Well, thank you.
Thanks.
So this is the last talk for 2023. We're back in January, so everyone have a safe holiday. And we'll see you in January. Thank you.